Hi kidlets, this is your notes video on the interior structure of the sun. I apologize that formatting turned out a little funky. It's not in the PowerPoints that you'll find on my website. And again, I apologize, this table covered up some of the text that is right behind it here, but I'll explain what it is. It's only one thing. So some characteristics about the sun, and if we do a comparison between the sun and Earth, we can see the temperature difference, pretty self-explanatory there. The mass, the diameter, but I want to draw your attention to the density because although the sun has a far greater mass, diameter, and temperature, the density is much greater on Earth. And that comes down to the composition that we have a rocky body Earth composed of heavier materials and elements, whereas the sun is composed largely of the lightest elements in the universe, hydrogen and helium, which are inherently very light, hence the low density. So the sun is about 100 times hotter. It's 300,000 times more massive, 109 Earth diameters, and over 1 million Earth volumes. And we can characterize the sun based on these distinct layers. So core is where we have energy production that happens at the center of our sun and every star. That energy production in the form of photons, then those photons have to leave the core through the radiative zone. We'll talk about the methods of heat transfer in just a moment. But radiation is the method that happens here in the radiative zone. We then have the convective zone, which underlies the photosphere. The convective zone is where we have convection, the process of rising and sinking of heat, then sinking as it's cooling down. That then underlies the photosphere, which is what we know as the surface. On top of the photosphere is the chromosphere, and extending outwards from the chromosphere is the corona. Notice that the corona does not appear to have any color here. Although we have three methods of heat transfer on Earth, the two which dominate energy production and motion within a star are simply radiation and convection. So what we have on Earth is conduction, which is through physical contact and motion of electrons. However, within the sun, we have that radiative zone, which is where radiation is the dominant form of heat transfer. And radiation is traveled through open space. That is also how we get our energy from the sun, because we're not touching the sun. It's not through the motions of rising and sinking. It is through photons leaving the core of the star and traveling through the radiative zone and outwards to the convective zone. And we'll see that in smaller stars and in larger stars, both the radiative zones and the convective zones have different sizes because they have either more or less of both. In much smaller stars, there is virtually no radiative zone. It is almost entirely convective, whereas in larger stars, you have a huge radiative zone. So convection, we can think about that as water boiling. So the process of when you get your bubbles on the bottom here, as it warms, that air inside the bubble expands. As heat rises, it makes it come to the top. Then you see, as it cools, the cold water falling. That is why you see the ripples on the top of boiling water. So this process also happens underlying what we call the surface layer of the sun. So the process of convection, we call this the convective zone. And one more time, we can see these layers here. You can definitely expect to be assessed on the different layers of the sun, being able to label those. You'll see this in your vocab packet as well. I would expect you to be able to know not only the names, but the processes that happen in each. So looking at greater detail of the solar interior, we're going to start with the sun's core. So although we say that the temperature of the sun is about 5,500 Kelvin, that would be of the external outer layers, whereas the core of the star has to have attained at least 1 million degrees Kelvin in order to have energy production in the form of fusion at all. So the core of our star is 15 million Kelvin. So all stars had to have had that core that reached 1 million to set off the stellar processes in the first place. So then within the interior, again, we have that radiative zone where you have the release of photons from the core traveling outwards to the convective zone through that form of energy transfer. And then we have the convective zone just beyond that, which is synonymous to like boiling fluid, except these are gases, and you have this rising and sinking. So I've mentioned a couple times the photosphere and how that's what we call the surface. And as we'll see, it's not actually the surface, but we call it that way because this is the only portion of the star that has its peak of the black body curve of radiation in the wavelength that we can observe in visual. And it happens to peak in the yellow-green portion of the spectrum. However, there are no green stars, so we see it as yellow. And again, there are no green stars simply because green stars also emit in the red and the blue portion of the spectra, and those two cancel out, so we only see white. So we call this a surface because this is what we can visually see. So here is where we would see things like these sunspots. We can see things like solar flares here. And we can also see the outward expression of this convection in something called granulation. So just like you have bubbles on the surface of boiling water, we can see that on the surface of the sun as well. In the photosphere, we can also see something called faculae, which are essentially these bright spots. They're too small to contribute to the overall intensity of the sun, so although they're brighter, they really don't contribute to the heat or the overall energy flux of the sun. But they can appear between solar granules or appear between granulation, and they're generally pretty short-lived convective cells, which can be several thousand kilometers across, and they're constantly forming and dissipating in timescales of just a couple of minutes. So here is an example of how granulation within the photosphere happens. And again, this is that simplistic model of convection, of rising and sinking. And the outward expression of that is granulation, or in singular form, just a granule. So here we can see what that would look like on the sun. And keep in mind that each of these bubbles is about the size of Texas. And here we can see some faculae that are between those. Those bright spots, those would be faculae. Traveling outwards from the photosphere, next we have the chromosphere. And this is a portion of the sun which can only be seen in the infrared portion of the spectra. So this is not what we call the surface because we can't see it. And until we had specialized telescopes, we did not see this or the corona. So here we have an increase in temperature. So if we were to look at a temperature profile of the sun, we would see the photosphere is actually the coolest layer, what we call the surface. And the temperature is steadily increasing outwards. So this portion of the EM spectrum associated with this is UV. So we can only see that then in eclipses or with specialized telescopes. So the chromosphere has two features. It has filaments and spicules. So spicules are these thin, wispy jets right here that look like fingers of gas, and they rise up from the photosphere. They can last about 10 minutes or so. And then filaments are areas that look to underlie CMEs. And as we'll talk about when we look at solar flares, these from the side are the same thing as prominences. And these are really important to the prediction of space weather. So the temperature increase within the chromosphere is likely explained by magnetic reconnection from sunspot to sunspot or within prominences that connect those sunspots. Our last layer of the sun is called the corona, and this is where we get the phenomena of the solar wind. Solar wind extends from the corona. So this area is comprised of small particles such as protons and electrons and ionized electrons as well, forming a plasma. This is emitted in gamma, X-ray, and UV, and because of that can only be seen in eclipses, or with a coronagraph that simulates an eclipse. So when I saw the solar eclipse last August, this is actually what it looked like. We could actually see the corona. Even just with the naked eye, that was what it looked like. It was incredible. So we have solar observatories that mimic this process of an eclipse in order to be able to view the corona and also the chromosphere. We can see the chromosphere as this red area right there, and we can see some flare and prominence activity right there. So we have to actually block out the rest of the sun in order to see the corona at all. The corona is the hottest portion of the solar atmosphere. We can see that the core is still bigger, but in terms of the solar atmosphere, this is the hottest. So this is 1,000,000 degrees, and the heating of the corona is still somewhat of a mystery to scientists. There are a lot of speculation, but no one is entirely sure. But it's likely due to the extremely energetic particles in that portion of the sun. And the term corona is actually Latin for the word crown, because this seems to form a crown around the sun. And the corona is essentially this aura or halo of plasma that extends millions of miles into space. And some of the features include things like these coronal loops right here. And the loops are essentially closed magnetic flux cousins of the open magnetic flux that can be found in the coronal hole, which are polar regions and that connect the regions of solar wind. Loops of this flux tend to well up within the sun, and they fill out with hot solar plasma. Because there is heightened magnetic activity within these coronal loops, a lot of times these loops can be the predecessors of solar flares and CMEs, which are solar mass ejections. So watching these and observing these coronal loops can be essential to the prediction of space weather, because as these tend to get larger and larger, these are an indication that a CME could be imminent. Active regions is something else we talk about when we talk about the corona. And active regions essentially connect these coronal loops. So you can see the loop itself, and then here would be the active regions. And we can observe these in imagery of the sun. And these would be areas that have opposite polarity. So we could say that this one would be positive and this side would be negative. So it forms a magnetic reconnection. And it generally is opposite to the polarity of the spots that are beneath them within the photosphere. And they're generally parallel to the equator. So these active regions all involve phenomena that's directly linked to the magnetic field. And these can occur at different heights above the sun's surface. The holes themselves, the coronal holes, are polar regions that are only visible within X-rays. These are pretty wide zones of the sun where the magnetic field is the same polarity or unipolar, and it opens towards the interplanetary space, or towards us. And these high-speed solar winds arise from these regions. So here we can see some pictures of the sun. This one is during an eclipse. This one is a coronagraph that's simulating an eclipse. And here we can see a CME event, which essentially looks like an explosion from the sun. And we have to block out the rest of the sun to see that. But this would be extending millions of miles into space. This is most likely an X-class solar flare or CME event. And by looking at those magnetic indicators within the corona, we can have some sort of indication of what the activity of the sun is. And as I've mentioned, solar physics is a hugely underfunded and understudied region of astronomy and astrophysics, and there's a huge need because we really only know the limits of our knowledge within the field of solar physics. There's so much more to know. And if we look at this temperature profile, we can see that down here in the photosphere is the coolest region, and then as we extend upward into the chromosphere, we have this sharp increase right here extending over to the corona. So right here is most likely due to an increase in electron activity due to those spicules and filaments extending upwards, exciting all of the different particles. And that is it for your notes. Have a great day.